All right, let's jump right in. Today, we are unpacking a really fascinating collision between synthetic engineering and real-world physics. It brings up this massive billion-dollar question: can a computer simulator actually predict the outcomes of a wildly complex real-world engineering competition? Our case study for this explainer is the DARPA Lift challenge, and all the data we're diving into comes straight from DBbun LLC's research paper and their R&D license terms. Let's get to it. To really wrap our heads around what we're analyzing here, we've got to start with the stakes. And wow, the DARPA Lift challenge was an absolute beast of a test. We're talking about roughly 100 top-tier engineering teams from all over the globe jumping into this competition. They were chasing a massive $6.5 million prize pool, and the mission? They had to build a vertical takeoff aircraft capable of lifting an incredible 4 times its own empty weight. That is a 4-to-1 payload-to-mass ratio. It's a target that literally pushes the absolute boundaries of modern aerospace engineering. But, physics doesn't really care about your prize money. Here is the harsh reality. Out of all those 100 accepted teams, guess how many actually managed to complete an officially scored course? Just 5. Yeah, the vast majority of these highly engineered drones either crashed or just completely failed to finish. And out of those 5 successful teams, not a single one of them actually hit that legendary 4-to-1 ratio. Let's ground ourselves in the real-world results for a second. DBrun took first place, walking away with $1.25 million after hitting a really impressive 3.84-to-1 ratio. MTech and Extreme Aerial followed up in second and third, and MacGyver placed 5th. We've also got Defentex in the mix here, who swung for the fences with a massive 6.11 ratio, which, sure, looked amazing on paper, but ultimately ended in a nasty crash. Now, the cool part is that before and during this actual real-world event, DBbun LLC was quietly running their V1.2 mission simulator. This is a physics-based engine specifically built to virtually and independently evaluate these exact types of heavy lift designs. Which leads us to Section 1, the plot twist, when the simulator got it backwards. Okay, so here is where the story gets incredibly strange. Researchers at DBbun took the public specs of those real-world drones, pulling from photos, videos, official standings, the whole shebang, and fed them into their simulator. They wanted to see if the virtual results would match reality. To fill in the gaps for missing data, they just used naive single-point estimates, basically human best guesses. And when they finally ran the numbers, it completely scrambled the real-world order. It declared DBrun, the actual real-life gold medalist, to be the absolute worst of the pack, and MacGyver, the real-world 5th-place finisher, the simulator confidently named them the absolute best. It was literally perfectly backwards. So, naturally, this begs the question, why on earth did the simulator get it completely backwards? Was this insanely complex physics engine just fundamentally broken from the start? Or was this an issue of human error in how the real-world data was being translated into the virtual world? Let's dive into Section 2, the methodological trap, fixing the blind spots. To their credit, the researchers didn't hide this embarrassing failure. They dug right into it and realized they had accidentally built themselves a methodological trap. By using those single manual human guesses for the missing drone data, they had been treating things like battery power margins completely inconsistently across the teams. The actual winner, DBrun, was accidentally given a virtually undersized power budget compared to the heavier drones. So how do you fix that? You throw out the human guesswork entirely and you bring in Monte Carlo sampling. Instead of an engineer just guessing one specific battery size, the computer randomly samples thousands of plausible setups from across a realistic range. By testing a drone across thousands of these randomized virtual missions, they stripped the human bias completely out of the equation. And as they were systematically sweeping through all these unknown variables, they finally caught the true culprit behind the massive variance. It wasn't the flight physics at all. It was how the simulator was sampling the battery limits. See, the total battery energy capacity was originally being sampled completely independently of the aircraft's size. Because of this little glitch, heavy drones like Extreme Aerial were randomly generating with physically tiny batteries. So they were failing virtually simply because they ran out of juice mid-flight, not because of any actual aerodynamic flaws. Now we're getting somewhere. Section 3, uncovering the true results, the simulator's real power. Once they spotted the sampling artifact, they quickly fixed it to make sure battery capacity was realistically derived from the drone's actual physical size. With the methodology fixed up, they reran the simulations. And the real result? Super illuminating. Even when perfectly corrected, fine-grained ranking agreement simply does not hold. The simulator cannot reliably predict exactly who is going to come in first, second, or third. So what's the big takeaway for your own projects? A simulator is an absolutely incredible screener, but it is not a magic oracle. When you're dealing with estimations of real-world specs, there's always going to be a limit to simulated exactness. But here is where it gets really, really interesting. They benchmarked those real drones against 100,000 purely synthetic designs generated by the software, and they found that every single human-engineered winning drone confidently landed right in the 70th to 77th percentile of the virtual population. They weren't hitting the 99th percentile, no, but they were solidly and consistently way above average. And this consistency becomes totally undeniable when we look at the MTech and MacGyver drones. Because of their specific multi-rotor designs, they were the only two aircraft whose exact physical architecture perfectly matched the simulator's logic. That meant zero architectural guessing was required. And where did they both end up landing? Independently, they both landed precisely at the 71st percentile. You guys, that is not a coincidence. That proves the simulator is an incredibly reliable screener of viable, real-world engineering. So let's put this to work in Section 4, Designing Better Aircraft, using the data. Now that we know the simulator consistently identifies good designs, we can shift gears to its forward-looking value. If an engineering team has a drone that already works, can they use this virtual space to actively improve their real-world winning design? Well, researchers used it to test modifications on the MTech drone. Just making the airframe 8% lighter on its own actually made reliability worse. But when they combined that lighter airframe with generous battery margins, boom, that pushed the MTech drone from a 3.66 payload ratio to a massive 3.98 to 1 ratio, while actually improving its reliability. That is dangerously close to DARPA's maximum full prize threshold. The simulator also independently discovered a vital design lever. By analyzing top-performing synthetic models, it suggested a really specific trade-off for the MacGyver drone. Basically, steal a little bit of power from the excess climb rate and invest that weight into building beefier, more robust landing gear. Running this change through the controlled simulation netted a huge 4.3 percentage point gain in reliability. It's a specific, highly testable design improvement. And crucially, the simulator also stops engineers from chasing ghosts. For example, population data initially suggested that higher cruise speeds correlated with success. It looked great on paper, but under rigorous, controlled virtual testing, increasing cruise speed didn't actually improve reliability at all. And in some cases, it even caused structural overload. It was a total false positive, and the simulator successfully weeded it out, which saves teams from wasting thousands of real-world dollars on the wrong upgrades. Let's wrap up the specifics with Section 5, the rules of use, DBbun's R&D license. So how does all this tie into the legal and operational reality of using such a powerful piece of software? DBbun released this dataset and the simulator, but it's under a very specific custom R&D license. The fine print is pretty firm here. You're permitted to use it for internal research and development specifically related to the DARPA Lift challenge, as well as for academic research, provided you cite DBbun. However, commercial deployment, operational use in production systems, and publicly re-uploading the materials, strictly prohibited. The wall between research and commercial exploitation is rock solid. In fact, if anyone wants to keep using this tool after the challenge concludes, they've got to sit down and establish a brand new separate written agreement with DBbun. Which brings us neatly to the core thesis of this entire case study. By embracing transparency and openly acknowledging their own methodological flaws, the researchers proved the simulator isn't a crystal ball, but it absolutely is a highly defensible screening tool and a powerful source for guiding real-world engineering. I'm going to leave you with this final provocative thought. Think about this for a second. The absolute best aerospace engineering teams in the world, backed by millions of dollars, engineered designs that confidently landed in the 71st to 77th percentile of this synthetic simulator. So we have to ask ourselves, if the absolute human limit right now is the 77th percentile, what on earth does a drone in the 99th percentile actually look like? The answer is out there in the data. Thank you so much for joining me for this explainer. Keep questioning and keep exploring.